force is acting in that direction. Then at this point, position vector point is r bar. R bar is position vector of this point, y and x. Okay. So how is this torque? Torque is defined as tau equal to r bar cross f bar. Okay. Why is that so? It is because you can calculate it as rf sin theta n cap. It is a vector product of position vector and force vector. Now you can see it depends on the force, magnitude of force. It depends on the position where you have applied. It also depends on the angle. Okay. So if this angle, what is this angle theta here? You extend it torque like this. This is the angle theta, isn't it? That is the angle theta. So all the properties of cross product are applicable for torque. Okay, this as tau equal to magnitude of torque r into f sin theta, or I can write it as r into f polar. What does that mean? R f into r sin theta. What does that mean? F into r perpendicular is the magnitude of torque. What exactly it means? F perpendicular means what? You can draw F perpendicular means this will be F perpendicular. Can you that this will be F perpendicular and this will be F parallel. Right? Parallel means parallel to the R bar. Perpendicular to the R bar. It is the perpendicular component which is rotating. Parallel component does not rotate. Are you understanding that? Parallel component does not rotate because it is pulling in the same direction. There is no way it can rotate. It is only the perpendicular which can rotate. That is the reason why it is defined as RF sin theta. Okay. Are you getting why RF sin theta is coming into picture there? It is the perpendicular component of force which is rotating that particular position vector. Or you could also write this, you extend the F, you can extend the F bar backwards. Okay. Then distance is, what is that distance? R perpendicular. That distance is R perpendicular. Okay. So you can write the magnitude of torque in any way you wish. Okay. It is R multiplied by perpendicular component of force to of R bar, or F multiplied by perpendicular component of R to the direction of F bar. Okay. So any of those things same. And what about the direction of the torque? Direction of torque is given by cross product. That is right hand screw rule or right hand thumb, isn't it? So when you are looking from the top of this rotation, let us say here, can you tell me what is the direction of torque in this particular diagram? What is the direction of torque? It will clockwise. It is clockwise. Clockwise means the screen or into the board, isn't it? It is into the board. So if this can be written as xi cap, I can write it as, so direction here, direction of torque will be into the screen. So it is minus k cap, you can write. Okay, it will be minus k cap. Okay, so direction of torque is given by right hand thumb rule or right hand screw rule. So that is the way torque is defined. We'll define, so this is the single point where the force is acting on a point. Okay, so torque of that force about point of origin, or in fact torque can be calculated about any point to be origin. You can calculate torque about this point. Okay, so how will I calculate torque about this point? Let us write. Let me write next. A, B, a force F is acting at position R1 bar. Find the torque due to this vector. Find the torque due to this force about R2 bar. What is the meaning of this position R2 bar and R? Let us say again, I can draw the diagram here, Y and X. See, R1 bar is something like this. This is R1 bar. R1 bar. Force may be acting somewhere in this direction. But you want that this point somewhere here, which is R2 bar. R2 bar is the, so you want to find the torque not about this point R2 bar. What will I do? I have to calculate torque about this. You take this as origin. That means basically take that as origin. So with respect to R2 bar, this is the position vector. Do you agree? This is R1 bar minus R2 bar. Okay. With respect to this point, position vector R1 bar minus R2 bar. Hence, you can say torque about R2 is equal to R1 minus 2 So torque of force acting at one point about any other point, you can always calculate like. See, no. Let me define what is known as couple. What is a couple? Two forces, two equivalent forces acting on a body make a couple or form a couple. Two equal and opposite forces acting on a body. Now there should be some distance between the two. Okay. If they are separated by some perpendicular or line of action of force is not same. What does that mean? Let us say you have one force here acting in this direction, F or minus F bar. F bar. So these two forces are acting at 2 points, equal and opposite. Their line of action of force, there is some distance between them. Okay. When it is like that, then we call it as a couple. Okay. Best example is when you are trying to open cap of a bottle. Okay, you are applying the force on both sides, equal and opposite force. Okay, that will try to rotate it. Okay, so what is the torque due to a couple? How will I find? To a couple, if you take this perpendicular distance is A. What is torque then? Torque due to couple is equal to F into A. I can say magnitude of torque. Torque due to couple equal to F A in this. What is A? A is the perpendicular distance between the two forces. A is the perpendicular distance between lines of action of forces. Okay. How do you get that relation? F equal to F into A. You can take origin at any point, whichever you choose to. Either on this line or it can be anywhere. Here, let us say take the origin here. You take origin here and let's say position vector of this is R1 bar. R1 bar is the position vector of first force. R2 bar is position vector of second force. R2 bar is the position vector of second force. Okay. Then let's say this angle is theta. We'll come to that later, that angle theta. See, what is the torque F minus F about this one? Can I say total torque? Net torque equal to R1 bar cross minus F bar plus R2 bar cross F bar. Is it correct? R1 bar cross minus F bar plus R2 bar cross F bar. That can be written as R1 minus R2 cross F bar. Right? R1 minus R2 cross F bar. Now what is R1 minus R2? R1 minus R2 is this vector from here to here. Sorry, R2 minus R1. That is, I have to write it as R2 minus R1. Here also can I write R2 bar minus R1 bar into cross F bar. So this is nothing but R2 bar minus R1 bar into F into sine theta. Here F is this force. So you can extend that and you can say that this is theta or this is also theta, isn't it? So that means that is, okay, I have to put magnitude here. Into F sine theta. But what is that is equal to F into magnitude of R2 bar minus R1 bar to sine theta. So magnitude of R2 bar minus R1 bar is this length into sine theta will give you A. Okay. So you can say that that is equal to F. Okay. That is the torque due to couple. Take any origin, doesn't matter. Torque due to couple, you will get the same value. Equilibrium rigid body. Sitting in the class and nothing else. How does it help? Tell me. Tomorrow's test, yeah, yourself. What are you doing? Not doing anything. Looks like you are not attention. You are not paying attention to what's going on. Are you? Okay. So equilibrium of a rigid body. What does that mean? We have learnt earlier equilibrium particle. Equilibrium of a particle means net force equal to 0. Okay. When it comes to rigid body, when force on a rigid body, it can translate as well as it can rotate. Okay. Depending on where you apply the force. Okay. Let's say for example, you don't have to write this part. I will write it again anyway. There is a rod like this which is lying on a smooth surface. In that case, let's say if I apply force exactly, then it will translate. Okay. But if I apply the same force somewhere here, then what will happen? It will translate as well as it is rotating. It's going to, after some time you will see that it would have moved like this. Okay. It will translate as well as rotate. Okay. So body under the action of a force, it can translate, it can rotate, both can happen. Okay. So when you talk about equilibrium, net force must be 0 and net torque also must be 0. We call that as total mechanical equilibrium. If a net force is 0, then we simply say translational equilibrium. Net torque is 0, we say it is rotational equilibrium. If both net torque both are 0, then we say that it is mechanical equilibrium. Okay. So equilibrium of a rigid body means if F net equal to 0, then we call it as translational equilibrium. What is the meaning of this F net equal to 0? If it is a three-dimensional, then F net along x-axis is 0, along y-axis is also 0, and along z-axis is also 0. Then if net to 0 under the action of multiple forces, then we call it as rotational equilibrium. Rotational equilibrium. If both F equal to 0 and net torque is also equal to 0, then we call it as mechanical equilibrium. Mechanical equilibrium. Let's take a simple example here. The rod, as I said, if you keep a rod on the smooth table, on a smooth table, you apply a force F in this direction, another force is also in the same direction. Okay. Does it? It doesn't rotate. It is in rotational equilibrium. Net force is not, net torque is 0. Net is not equal to 0, but net torque equal to 0. Why? How can you say it is 0? Because if I take, let's say, this point on the body, the force above one, it is trying to rotate in the clockwise direction. The same amount of torque is applied by the below force, which is trying to rotate in the anti direction. So net torque is 0. So I call it as rotational equilibrium. Rotational equilibrium. Now the same forces, if I apply this way. In that case, net force is 0, but net torque is not 0. Now it becomes a couple, so it's going to rotate. Okay, it will not translate, but it will rotate. So we'll say that F net is equal to 0, but tau net is not equal to 0. So we can call it as translational equilibrium. Now we apply same force, both forces in the middle. Let's say you have here exactly same force in the opposite direction. Okay, now it will neither rotate nor translate. Okay, this is called translational equilibrium or mechanical equilibrium. F net equal to 0, tau net is also equal to 0, then we call it as mechanical equilibrium. Now you also have finally the concept of center of gravity related to gravitational torque. Okay, just briefly mention that. What is center of gravity? Center of gravity is the point where you expect entire gravitational force on the body to be concentrated. Okay, center of gravity is the point where, I will simply write, force on a body to act. Okay, how do I define that center of gravity? Center of gravity is divide that body into small mass particles. Okay, so the definition wise, center of gravity is, you can say, of gravitational torques on all mass particles body about center of gravity is 0. Sum of gravitational torques of all mass particles about center of mass gravity will be 0. That position is called center of gravity. In other words, weight is supposed to be active. Total weight is nothing but sum of total gravitational force, isn't it? In other words, we can also say that equivalently, center of gravity. See, for us, from objective point of view, only one simple point that is important for us is center of gravity will coincide with center of mass for bodies which are small in size compared to size of Earth. If the very large compared to size of Earth, then mass and center of gravity may not coincide. That is the only point you need to be remembering about this concept. Other than that, of course, we'll do some problems, but theoretical bit is only that one. So, of gravity coincides with center of mass for small bodies. That means whose size is small compared to Earth. For very large bodies, what is the difference? Difference is if body is very large, then what will happen is gravitational forces on that body, if this is Earth, let us say, and you have a body like this, is large enough. Okay, let's say this is the body, in which gravitational force, now it is very large body, now you can say that gravitational force is in the same direction. It will always act towards the center, isn't it? It will always act towards the center. For a small body, you always say that gravitational force in the same direction. Okay, so there is a difference. Okay, gravitational force for a small body acts in the same direction of for all particles, whereas large bodies gravitational force direction is different on different particles. Okay, because of that reason, center of mass and center of gravity may not coincide large body. Otherwise, they will coincide. Okay, so that is a simple bit that you need to be aware. It is we have another 5 thought. Okay. Now let's also talk about introduce the concept of angular momentum. We'll just introduce the concept of angular momentum of a particle. Okay. So let's talk about that. L bar particle moving with velocity. How do I define? See, in rotational motion, as we said, talking about bodies rotating, angular variables we need. All angular variables, first you define for a particle, single particle, and then you extend it to the, okay, that is the general idea. So here also we do the same thing. Angular momentum you define first for a particle, means small mass which is having mass but size is, isn't it? So you define like this. If particle particle is moving with speed v, mass of the particle is m, speed of the particle is v bar. Speed is v bar means what is its linear momentum? V bar equal to m into v bar, isn't it? V bar at certain point, let us say its position vector is given by r bar. Position vector is given by r bar. Then the angular momentum is defined as, actually you can also call it as moment of momentum. L bar of the particle about r is given by L bar equal to R bar cross P bar. R bar cross P bar, or you can write it as R bar cross MV bar. What happened? Anoop. Sleeping simply. What about that girl? Second bench. Is sleeping from the beginning. Hmm? Come on. She's again sleeping. Not feeling well. Okay. So we can use the same way. R bar equal to, we can write it as RMV sine theta, isn't it? L is what? R sine theta or RMV sine theta. What is theta here? The same way, this is angle theta. You can write, you can exactly write the same way as we did. That means RM into, can we write M into R into M into V perpendicular, or M into V into R. Both means same thing. Exactly the way we did for torque, you can write the same way angular momentum also. Okay. See, the concept of momentum is important from the objective point of view. The questions asked are something like this. Okay, first let us take few examples of question. Example 1, let us say angular momentum of a particle moving angular path with constant speed. What will it be? Circular path of radius r. What is angular momentum? If it is moving in a circular path, simply you can write mvr because theta equal to 90 degrees. Let's say it is moving with speed v. This is r bar, right? At any point, okay, you can write L bar equal to R bar cross MV bar, but magnitude if you want to write, see what is angle? Angle is always 90 degrees. Okay, at any point, angle is 90 degrees. So magnitude is MVR sine theta is equal to MVR sine 90 is equal to MVR. That is the angular momentum of a body circular path at a given instant of time. Example 2, time is over. Okay, we'll stop here.